Alright folks, this last video lesson is going to cover something called reaction mechanisms. This is a rather lengthy video process and there's lots to say, so buckle up. Here we go. What I'm going to talk about is what is a reaction mechanism. If you knew it or not, up until this point we've been showing you chemical reactions, and those chemical reactions are what are referred to as net reactions. Reaction is an overall reaction, so basically all it's doing is showing you the reactants and it's showing you the products, showing you any of the details or any of the side reactions that may have happened that add up to make the overall net reaction. In fact, many chemical reactions are in fact a sum of smaller reactions put together. These small reactions are referred to as elementary steps. And a reaction mechanism is an order in which those elementary steps happen. And not only do reaction mechanisms tell us the order in which these steps happen, but also their relative speeds. Each elementary step has a corresponding speed associated with it, but none of the elementary steps necessarily happen at the same speed. You might have remembered from a previous video lesson that I said that the rate law for a net reaction can only be determined experimentally. That remains to be true. But rate laws for elementary steps can actually be determined based on the stoichiometry of the elementary step. And you might think that the fact that rate laws for elementary steps can be determined using stoichiometry seems to not make sense or is a contradiction, but in fact it very much explains why rate laws for net reactions cannot be determined using stoichiometry, because a net reaction does not tell you about the steps that are involved in producing the products desired, and so you can't assume that the stoichiometry that you see in front of you is the exact reaction mechanism of the reaction itself. But when you break an overall reaction or a net reaction down into its elementary steps, it very much follows the stoichiometry of those elementary steps itself. So we indeed use the stoichiometry to determine the rate law for an elementary step. Now this table down here shows the different types of elementary steps that you would encounter. Let's take a look at each one of these individually. Now it is well known that in order for a chemical reaction to happen, and we're going to be referring specifically to elementary steps from this point forward, but in order for a chemical reaction to happen, the reactants need to come in physical contact with one another, if there is indeed more than one reactant. Reactants that you need to react in order for a reaction to occur, the less likely that that reaction indeed will occur, because you have to come together in just like the perfect instant where two or even three molecules or atoms and combination of reactants need to touch each other all at the same time. So as we work from the top of this table down to the bottom, a unimolecular and bimolecular situation is very common, but a termolecular is very unlikely. So let's start with a unimolecular. Let's say, for example, you have just a single reactant and it's decomposing into a product. The rate law for that elementary step is first order. The rate is equal to the concentration of that reactant that you began with times the K constant. Step up to bimolecular. Now that could come in two different forms. What if you have two of the same reactant coming together to produce a product? Maybe you have an elemental oxygen and an elemental oxygen coming together to make diatomic oxygen as the product. If that's the case, then that one reactant is second order with respect to that reactant in a bimolecular situation. It's more likely that you have two different reactants combining to form one product or two products. In that case, the rate law is dependent on the first order concentration of A and the first order concentration to be added together gives you second order or bimolecular sort of scenario. Now, as we talked about just a few seconds ago, termolecular scenarios are very rare because you have to have, once again, three things coming together all at the same time with the correct amount of activation energy in order to create that activated complex, in what we talked about in the last video lesson or a couple video lessons ago. So not only do you need three things coming together at the same time, but they have to have the correct amount of energy, the minimum activation energy for that to happen. If only two of the three collide at that time, then that product is not going to happen. Or if they collide but not with enough activation energy, then that reaction will not produce products either. So termolecular scenarios are very rare, but as the pattern has shown, If you have three of the same substance coming together, that is third order. Or if you have two of one substance and one of another, that's also third order. Second order with respect to A, first order with respect to B. Or three unique substances producing a new product in a sort of situation like synthesis. You have three things all first order with respect to first order of each of them adding up to make term molecular, or the rate law being third order. There's a reason that we don't actually have any graphs or integrated rate laws for third order reactions, is because they're very, very rare. Most likely scenario you will see in the upcoming reaction mechanisms is that you'll see unimolecular and bimolecular sort of rate laws for the elementary steps. So let's take a look at what a reaction mechanism would really look like. First thing that you will be presented with is the overall reaction, which is usually written at the top of the problem. The next thing that will be presented to you are the elementary steps, and not only will they be presented to you, but they'll be presented in the order in which they occur. As I mentioned on the last page, they're either going to be unimolecular or bimolecular. Very rarely will they be termolecular reactions. Now, if you take a close look at these elementary steps, what you'll see is that if you add them together, they will in fact equal the overall reaction on the top. And there will be no parts left over, no parts unused, and you'll always have just the right amount of molecules to equal the overall net reaction. Sometimes you'll be asked to prove this, or you'll be asked to show this by simply adding the reactants and product sides together. So if you look closely, I've got NO2 and NO2. So in fact, on this one side of the reaction, I have two NO2s. Also, I have an NO3 and a CO. Now on the product side, I have an NO3, I have an NO, I have an NO2, and a CO2. Now what we can do now is combine like terms by multiplying or canceling things out that occur on both sides of the reaction. And if you look closely, I've got an NO3 and an NO3. NO3s in this case are considered to be intermediates. And what an intermediate is something that gets produced in one elementary step, but then gets used up as a reactant in the second step or a step after the first. And so because NO3, it gets produced in the first and used up in the second, it is considered to be an intermediate. And it gets canceled out of the net reaction as a result. Now something else you might see is that I have two NO2s on the left and one NO2 on the right. So one of them is going to cancel out. One cancels out on the left, the only one on the right cancels out. But the fact that I had some NO as a reactant and some NO as a product in my net reaction means this is in fact considered a catalyst. A catalyst by definition is something that is in the beginning of a problem or in the beginning of a chemical reaction is present, and it's also present in the end. And its only purpose is to facilitate a reaction to perform. And so in this case, the catalyst is NO2. Now it happens to also be one of the reactants in the overall reaction, but only some of it gets used up. Some of it is catalyzed, and another part is actually sticking around. So if anything starts a reaction and ends a reaction, meaning it starts as a reactant in step 1 and ends as a product in step 2, that means it was there at the beginning and produced at the end, then it's considered a catalyst. Of course, it cancels out of the final reaction, but is considered a catalyst. But if something is produced in reaction 1 and used up in reaction 2, that is called an intermediate. So quickly, I jotted down the definitions of both. An intermediate gets produced in an early step and then promptly gets used up in a later step, whereas a catalyst is present as a reactant in an early step and then is present as a product in a latter step. In both cases, neither the intermediate or catalyst make it into the final overall net reaction.